Do you see my slides correctly on Zoom? Yes, okay, good. So last week we studied the IP layer. What we're going to see now is how the IP layer merges with the MAC layer and how there are some points of frictions between the two. So the topic is MAC address resolution. What is the problem? When a machine A has a packet to send to a machine B that I call next hop. Next hop means seen from the viewpoint of the MAC layer, B might be the default router, or it might be that the packet is on the way between two routers, so the packet is going from one intermediate router to the next. So we are in the case where a machine A has to send to what is called by IP the next hop. Right? In order to do that, we must use the MAC layer. The MAC layer uses addresses, so we need to know the MAC address of the next hop, right? Which is not information that's available at the IP layer. We have seen that an IP host must be configured with its own address, mask, DNS, address of the DNS server, but doesn't contain the MAC address of all the next hops which it can communicate here. So it needs to get it. How does it get it? Well, it's plug and play, of course. You don't need to configure it. You could configure it. In the lab, we will see the ARP command that allows you to configure, for example, the next hop MAC addresses, but in principle, you don't do that. So there is a procedure which is called address resolution. The idea is that the host A sends a question on the local area network asking who has this IP address? And then all hosts will receive it. All hosts that should receive it, that might have this IP address, will receive it and will hopefully reply with their address. So that is the mechanism that is used. Here is an illustration with IPv6. I'm showing here a diagram that shows a line, which is a schematic representation of an Ethernet network. It might be an old-style Ethernet, where the devices are physically connected to the system. It can be a local area network that is truly a joint cable, for example, if we use power line communication, or it can be a Wi-Fi network. So A wants to send a packet to B, so A knows the destination address of B, which is this long, for IPv6, is this long string of hex digits here. Of course, if this happens, it must be that B is in the same LAN as A, in IP terminology, in the same subnet. Otherwise, there would be no reason to do this. So A will send a packet called neighbor solicitation packet, which is part of the neighbor discovery protocol. One ugliness of IPv6 is that there's lots of complicated acronyms. So when we do Wireshark, we will see that as an NDP packet, which is part of the ICMP protocol. Remember, ICMP is a protocol that is used to manage the IP layer. So that's an example of management of the IP layer. So it sends this packet. This packet is simple apart from its address. It's simple in the sense it contains inside what you can imagine. It is a question, who has this IP address? So it contains the target IP address as part of the payload of the packet. And now the only interesting question is, to whom is this packet sent? So this packet with IPv6 is an IP packet. Every IP packet must have a destination address. So what is the destination address? To whom do we send it? A simple answer could be to everyone who is a potential receiver. Who is everyone? That should be everyone that is on link, that is in the same LAN. So we could use the multicast address that is used for IPv6, and that means everyone in the same LAN. For IPv4, it would be the address that has only once, 255, 255, 255, 255. We could do this, but we don't do this. We do something that is believed to be smarter, which is using what is called the solicited node multicast address. So the solicited node multicast address, that I will explain here, is an address that is made to reduce the number of devices that will receive it. Let's first see how it is made. So we take a prefix, which is this prefix of 104 bits. So 104 bits means there remains 128 minus 104. There remains 24 bits that are freely available. 24 bits, that's how many hex digits? 24 divided by 4, that's 6. So that means there's this prefix, and then the only thing we can add to this is the last 6 hex digits. So what do? Is we take simply the last 6 hex digits of the target address. Remember, A is asking who has this address. It's the IP address of B. So what A will do is take the last 6 hex digits of the target address and puts them into this multicast address, and this is the solicited node multicast address. Now, who will receive this? Bonjour. We're trying to have the beamer. En fait, il est connecté à celui-ci. Who will receive this packet? Well, all hosts that subscribe to this multicast address. We will see a bit later when we talk about multicast. The way multicast works is that you need to actively subscribe to a group. By default, the operating system of any IPv6 machine automatically subscribes to all the solicited node multicast addresses that have the same 24 ending bits as the IP addresses of this machine. In this case, certainly B will receive it. C and D might receive it, but for this to happen, they should have the same low order 24 bits here. And the idea is that this is unlikely to happen, because in a local area network, you tend to differentiate the end systems by the low order bits. So it's not strictly impossible to happen. You can have a numbering plan that gives the same 24 bits to all hosts in your system, and you differentiate them only with slightly higher order bits, but typically you don't do that. So you use the leading bits to identify the system. We will see also that with IPv6, we very often use random numbers for the last 64 bits. So if that happens, the probability that 2 hosts in the same LAN have exactly the 24 same bits, when the 24 bits are taken by chance at random, this probability is 2 to the minus 24. So it's an astronomically small probability. Okay, Beamer is back. Wow, what was the problem?
The connector.
Cabling problem, which is a good introduction to the next topic, which will be the MAC layer that is trying to solve the fact that cabling is always a nightmare. And when something does not work because of a cabling problem, usually it's the last thing we find. We will try everything else before. Yes? Merci beaucoup. C'était peut-être ça aussi la première semaine quand ça ne marchait pas. Yeah, we came for a dry run the day before, it didn't work. Okay. We called someone at your service and they fixed something. Oh, c'était vous. Okay. Okay, so let me do a change of screen. Merci beaucoup. I just need to make sure. Do you? I'm not sure I see it. Display setting. Do you see anything? No, I don't get it. Yes, ça marche. Ah, that's much better. So the idea, instead of using a broadcast address or everybody in the LAN, is to have something that will perturbate only a small number of hosts. Imagine, for example, you would have a printer in your LAN. If you send broadcast, then whenever anybody does an address resolution, the printer receives it. So, which perhaps is a low-performing processor on the printer, so you would not like to have that. Then the rest is as expected. B hopefully will respond with a response, which is called a neighbor advertisement, which contains, in the text, contains its own MAC address, this one here, and the neighbor advertisement is now sent to A's IP address. We can do that because there is the source address and the packet sent by A. Est-ce que je peux mettre? I stopped sharing, okay. Oops, I was sharing the wrong screen. Thank you. C'est la beauté du direct, on dirait en français. So A will receive the packet and now knows the MAC address and now can send the intended packet to B's IP destination address, of course, which it already knew, but now it knows the MAC address. And as long as it did not have this MAC address, B could not receive the packet. So whenever you have to send an IP packet, you need to do all that stuff, at least once in a while. Obviously, you don't want to do that for every packet that you send, so you keep the result in a cache. So A will keep what is called a neighbor cache. So with IPv6, every host keeps in memory, in temporary storage, keeps everything it knows about all the neighbors with whom he talks. So A will keep in this neighbor cache the MAC address, and it will refresh the cache whenever there is evidence of communication that works. What is evidence of communication that works? Well, whenever A receives a packet from B, for example, which will invariably occur, because if A sends something to B, quasi all applications are both ways. Even if you stream thing in one way, there is always TCP acknowledgements in the reverse direction, for example. So A is likely to receive traffic from B. So if A and B are streaming things, if A is streaming things to B, for example, the cache will never expire because once in a while, A will receive a packet from B that will confirm the MAC address of B. This is how things are organized. Now, of course, if the systems go completely idle, this will expire and will need to be refreshed. For some reason, I don't get the quick. With IPv4, the same happens with a few anecdotal differences that show up when we do Wireshark. It's similar, so the same principle, except the names, but that's general. IPv6 renames everything, which is a pain, but, and you will see much technical literature uses the IPv4 terminology. So many people will call what I call an NDP NSNA exchange, they will call it an ARP exchange. ARP is the name that was used for IPv4, and it stands for Address Resolution Protocol. Interestingly, ARP is not an IP protocol, which means when an IPv4 host asks to another IPv4 host, what is your MAC address? It doesn't use IP, which today seems odd, so IPv6 uses IP for that. But remember, IPv4 was done in 1974. At that time, there were lots of other protocols. AppleTalk didn't exist yet, but there were DECnet, SNA, etc., LAN protocols for what was called DOS, the pre-Windows world. And address resolution was a common problem of all of those network protocols. Therefore, there was a universal address resolution protocol that could work for any protocol, not just for IPv4. This is how the world was in the 70s here. So ARP for IPv4 is a standalone protocol, which is visible in the fact that it has an Ether type. It is an Ethernet frame with an Ether type, which is for ARP here. And the major difference is we don't use solicited node multicast addresses. Of course, we don't do such exotic things with IPv4. Why? Well, there's two reasons. First, at the time it was done, nobody was worried about broadcasts. All the protocols invented in the 70s use broadcasts extensively. Now we are very much worried about broadcasts. So we try to avoid them because they perturbate other machines. They're also easier for attackers to use. And the second reason is that IPv4, we don't have that many addresses. So that burns a large space of the address space just for those special purpose multicast addresses. So we don't do that with IPv4. So if you look inside an ARP packet for IPv4, you will see, for example, the destination address, which is all ones, that's the broadcast address, which of course stays in the same local area network, it's the linked local broadcast, and a protocol type that says it's not an IP packet, but it's an ARP packet here. And then it contains text, which is what is the target IP address. So this is an ARP protocol where this machine is trying to find the MAC address of that machine here. We find also a useful convention that whenever we don't know an address and there is a field that needs to populate the address, we put zeros. That's a universal convention in networking here. Good. So let's start. To conclude on this topic, let's try a little quiz. M1, which is on the left here, has a packet to send for M3. And assume that N1 is just booting and has emptied all its caches. What will happen? I close the poll in a few seconds. And the majority says B, which is the correct answer. Large minority says A, which is incorrect. Of course, when M1, here we have two LANs interconnected by a router. In IP terminology, we have two subnets. We must have two subnets in principle. Therefore, when M1 sends a packet to M3, the destination IP address is M3, but M1 will send it to the next hop, which is the router. So the problem of M1 is not to find the MAC address of M3, but the MAC address of this interface of the router, which is P.1. In particular, M1 will never know what is the MAC address of M3, except if you have a spyware or some application program that speaks directly to M3 and asks M3 to look inside its MAC address, but just by looking at traffic coming from at M1, you will not know what is the MAC address of the remote destination, obviously. If you're a bit interested in security, you should be worried about everything I presented here. We're saying essentially, if I'm on Wi-Fi and I want to send to someone else, for example, in this room, then my computer will simply ask everyone, give me the MAC address of this destination address. Of course, if there's a bad guy in the room, this bad guy will also receive the information. And if this bad guy has a very powerful and very fast processor, perhaps will receive it before you and will respond with his or her MAC address. So we will have a good way to do traffic, to capturing traffic. So that's the problem. Now, ARP and NDP are not secured in this way, so it is true, and this will happen. So how could we prevent this from happening? Well, there is simple methods that are called, for example, DHCP snooping. We will see what DHCP is in a minute. But the idea is that if you are on an Ethernet, not Wi-Fi, but if you're on Ethernet, then in order to connect to the Ethernet, you probably go to a switch, and the switch knows probably everything about you because there is one port per device. So the switch can observe what is the MAC address that is going on this port. And except if you do your local Ethernet at home, if you do your local Ethernet at home, this thing will happen, but you hope you are secured, you know your cables and the cables don't go outside. If you have a large-scale internet or an enterprise Ethernet, then you want more security, and typically at EPFL, for example, you cannot come to a random Ethernet plug and connect your device. The EPFL wants to allow certain MAC addresses on some plugs or some Ethernet sockets. So this is a way of what is called a managed Ethernet network, where since we go via a switch, we can say this Ethernet socket, which is in my office, for example, they know what are the MAC addresses of the different devices I use. And if I change my PC or if I change my Ethernet adapter, I will need to say to my system manager that they need to inform the networking systems of EPFL to allow this new MAC address. Well, otherwise, it will not work. So those are managed networks. In such managed networks, of course, the switch knows the MAC addresses of everyone. So in such networks, the switch will capture the ARP or NDP-NS packets and will directly reply to them. So will act as a proxy. So the ARP packets will not be forwarded to everybody. So if there's a bad guy connected to Ethernet somewhere, the bad guy will not receive any of the broadcast or multicast packets. Instead, they will go directly to the switch that has access to the list of all the MAC addresses that are authorized, knows what also the IP address that correspond to them, and will give the response here. That's a managed system here. So it's deployed in enterprise networks, rarely in homes or Wi-Fi access points. So in Wi-Fi access points, typically the problem can occur. So somebody could capture your traffic. This is one of the reasons on Wi-Fi access network, you should not assume that you're secure. So you should assume that somebody can get your traffic and can read it in particular or manipulate it. So you should use some kind of encryption and authentication that we will discuss a bit later. There is an alternative to that, which is called secure NDP or secure ARP, which works with IPv6, which consists in attaching some secret with the IP address here. So the IP address is typically made of two parts. Here you recognize the beginning, which is EPFL, means EPFL. There is typically one A6, that means the subnet inside EPFL. And the leading 64 bits, which is this part here, is the host part, the one that is of interest. The prefix is completely known, so there is no secret about it. If I am in this subnet, I know the subnet prefix. So even the bad guy knows, everybody knows it, it's completely public what the subnet prefix is if you are in this subnet. So there is no point protecting it. But the host part, for example, typically the 64 bits when we use this system, is cryptographically assigned, can be a cryptographically assigned address. So the host part is called the EUI, end user identifier, which can be assigned randomly or can be assigned through management, so somebody gives it to you, or can be derived through some cryptographic means from a combination of public key and private key. What is a public-private key pair? Well, cryptography uses keys. The simplest forms of cryptography use, which is called symmetric cryptography, uses a key for encrypting a message. So you have a string of bits, you shuffle them, and with a key, you make a a completely ununderstandable message. And in order to decrypt, you use the same key. You do the reverse operation with the same key. That's symmetric cryptography. Most of cryptography is done in this way. That's the only one that is fast today. There is another form of cryptography, which is way, way smarter, and on which we depend also, which is asymmetric, which allows to encrypt with one key and decrypt with another one. And furthermore, it is possible that to make one of the two keys public. So there is a private key, little p here, that of course should be kept secret. You can algorithmically derive the public key from the private key, but not the other way around. Of course, if the key is long enough. So those keys are typically for several hundreds of bits. With RSA, you need 2,000 bits. It's what is called a one-way function, deriving for example, with RSA, deriving the public key from the private key simply requires doing some modulo operations and multiplications and exponentiations. But deriving in the other way around the private key from the public requires factoring into prime integers the public key, which is a hard problem if the public key is 2,000 bit long and we don't have quantum computers. We still don't know how to do that today. So to make a long story short, if we use asymmetric cryptography, we can have two keys and one of them can safely be made public and the other one secret. And furthermore, I know that if I receive something that is encrypted with a private key, and if I can decrypt it with a public key, I can be fairly sure that only somebody who owns the private key could have encrypted this message here. Because if the encryption worked, if the decryption worked, and typically we use that for a signature. A signature means I encrypt a text and that contains a checksum, and I give you the checksum in clear text, and you try to decrypt it with the public key. If you decrypt it with the public key and you find the same checksum as the one that was given in the clear text, then it means it worked here. So how does it work here? The network advertisement message, so the ARP reply that is sent to A, contains a signature of a number of things computed with a private key. So it contains the MAC address, but also a signature that shows that this has been sent by a system that owns the private key. Why does it help? Well, because the IP address is derived algorithmically from the public key and a few other things like the IPv6 prefix by an algorithm that is public. Anybody can do it. So I'm looking for your MAC address. I know your IP address through some mechanism. I've obtained it by a web interconnection or a source address or some kind of mechanism. So I know your public address. I must know also with this system your public key. So I can verify, I can bind the two together because this algorithm is known. So I must be sure, I will be sure that the message, the reply that I've obtained is sent by somebody who owns the private key. So the bad guy can receive the ARP request, but can do a reply, but the bad guy will sign the reply, but the signature, I will not be, when I will verify it with a public key that corresponds to this address here, will not match because the bad guy is not able to forge a signature unless he or she owns the private key. Of course, the bad guy can still infect your computer and steal your private key, but in that case, that would. So this is a solution. It's not widespread yet, but some systems start to derive this. Voila, that's what we saw about MAC addresses and how they interfere with the IP addresses here. Next thing we want to discuss today is how we configure automatically hosts here, host auto-configuration. We know that an IP host needs all of this information that we've discussed already. How do you get it? You can always get it manually. We do that in the lab for some of the manipulations we ask you to do. But typically you do it using DHCP or what is called stateless auto-configuration. So IPv6 typically uses both, and IPv4 typically uses only DHCP. So DHCP dynamic host configuration is very simple. It simply means that when a host boots, like my machine boots here, I'm showing it with IPv4, it wants to find its MAC address, its IP address now. So what will it do? Well, a bit like ARP, it will send a message to the DHCP servers. So DHCP server is a server. For example, at home, it will be your ADSL modem, if you have ADSL at home. That contains a block of available addresses here. So it will say, of course, you must configure it with a prefix. You must choose a prefix, but at home, for example, it's done by default. It's a private address, set of address, and it will say a block, for example, half of the all possible addresses can access in this subnet. I make them available to whoever asks. So if you have a visiting person who comes to your house, that machine will try to obtain an IP address. So it will send an IP packet, which is broadcast, as you see here, with IPv4. Of course, with IPv6, it will not be broadcast. It will be sent to the multicast address of all the DHCP servers that are on link. So as you can imagine, IPv6 has one multicast address for every type of use. In IPv4, we don't, so we broadcast it. So it's like shouting and saying, I am new, I'm coming, I don't have an IP address. So the source address in this packet will be 0. It's the only case we would see a 0 source address, which means it's an invalid address, which means there's no point responding to that source. Okay? With IP, of course. But of course, when you will respond, you will respond to the MAC, to the IP address that you will find, because you are the DHCP server. So the DHCP server has a list of IP addresses that have not yet been allocated in this local area network. We'll pick the next available one. Or perhaps you have a more managed environment where you know every MAC address or every particular information on this device must correspond to this specific IP address. You typically do that at home. If you have a server, for example, you want that the IP address of the server remains the same always, so you can have a static table in your DHCP server. Whatever happens, the DHCP server, here I'm showing a relay, but imagine it's a server, will choose the next available IP address and send a reply to this client. Now, to this, the destination address will be the IP address that's given here. And of course, the MAC address must be the MAC address of this client. How does the server know the MAC address? Well, it has received a request. So it knows the source MAC address from the request. So it knows the MAC address here. As I showed it, it requires that I have a DHCP server in every local area network, which is what happens at home. Typically in a small network, you have only one subnet and you have a DHCP server for this subnet. At EPFL, we don't have one DHCP server in every subnet. There are tens of subnets. You don't want every, a subnet is typically a floor. You don't want every floor to have one subnet. The Wi-Fi network is also divided into a large number of subnets. So instead, there is a trick. You have one enterprise-wide DHCP server, and you have what is called a DHCP relay function that is typically added to the routers. Again, it's a proxy type of function. I repeat the scenario we said before. This host is trying to boot, so it shouts and say, I would like to have an IP address. It sends it to whoever wants to receive it, whoever is a DHCP server or relay. The router, the box that I call the router, but it's not a router function. It's not analyzing an IP packet based on its IP destination address. It's doing something. It's receiving this packet, which is a UDP packet, to port 67. So it goes into a small application program into the router that receives the packet, sees, oh, this is a DHCP request. Somebody wants an IP address. Your router knows the IP address of the DHCP server. So your router will remember everything, keep that in memory, ask the DHCP server the same question, will get the reply, and then will reply to the client. Of course, if your router crashes in between, the whole process will be dead. You will have forgotten, lost the information, and the client will need to start again. So this is an example of two things. First, of a proxy function. We see that the middle box here acts as a DHCP proxy for the client it appears to be the server, and for the server, it appears to be the client here. So that's typically what a proxy does. And another thing we see is that what we call a router, which is formally the function that does the intermediate job of the IP layer, is sometimes overloaded with other functions. So we will continue to call it a router, but this has nothing to do with the IP layer. It's really an application that is running on the router here that does things. So we see a router will receive packets to UDP ports here. So this is DHCP. The same works with the with IPv6 with obvious differences. With IPv6, there is typically another thing that always happens. It's called stateless address configuration, SLAC. With IPv4, that normally does not happen. When with IPv6, it always happens. With IPv4, you don't have many addresses. You're happy if you get one. So you typically ask the DHCP server and you get it. With IPv6, we have plenty of possible addresses. The address space is practically unlimited. So what we do with IPv6 is we use always what are called link local addresses. So every host, when it starts, when it boots, will associate to itself a linked local address. So a linked local address, we have seen this concept last week, is an address that's valid only within a subnet. What a host will do is will try to get one, depending on which operating system and which version of the operating system, it will use one out of a large number of methods. You can manually configure your host, for example, to get an address that is one if for a certain host. There is a default method that builds a MAC address from an end user identifier, a 64-bit token from the MAC address. Essentially, it takes the MAC address and it pads it with 16 bits to make it 64 bits. This is not very much used today. What is very much used is a randomly assigned address. So when the host boots and wants an address, it will draw a random number and say, this is my address. And we have seen also the cryptographically generated address if the host has a public and private key pair associated with it. Of course, when you do that, in particular with your random address, there is a minuscule but non-zero chance that someone else has exactly the same. If you draw 64 bits at random, the probability is truly astronomically small. But if everybody does it, there are billions of hosts in the world. If all hosts do it once in a while, sooner or later, there will be a case where there will be a collision. Another host has the same address as you. There can also be collisions due to other reasons that are more likely to occur due to errors. For example, if you have manually assigned it and there's an error, somebody else has the same. So you always perform what is called an address duplication test by sending a packet to all hosts who are likely to have the same. With IPv6, we would use, guess what? The solicited node multicast address. You build a multicast group from the address that you want to acquire, and you will ask all people who have the same 24 low-order bits as this address that you want to acquire. If one host replies, it means that host has this address. Question?
Is this request limited to the subnet? Or...
The question is this request limited to the subnet? The answer is yes, of course. Everything that is being done, because we're configuring a linked local address, we're interested only in collisions inside the subnet. So of course, this solicited node multicast address is a linked local address always. It's broadcast only within the subnet here. It's multicast within the subnet. So you will do the address duplication test. If the address duplication test fails, well, the address allocation fails. So typically the machine will not boot and it will not work. So you will need to fix something. Try again if it was a random address, which means rebooting the machine, which is a universal recipe for problems with computers. Otherwise, it might be a problem in the configuration that you will need to fix it. So this is always done by all IPv6 machines. Sometimes you will also try to do more depending on how it's configured. If you want not just a linked local address, but your global address, there is a way to do it also by asking, is there a router in this local layer network that is willing to act as my default router? This is based on the idea, which is true in practically always, is that routers are managed by different entities than hosts. Right? If you, at home, if you have your ADSL modem, it was managed perhaps by you, if you configure it, or by Swisscom, if you got it from Swisscom. So it was pre-configured with a prefix that will be given to your home and everything here. So EPFL is the same. All the routers are configured by the network systems of EPFL. Your machine or my machine are configured in the best case by an IT specialist of our lab, in the worst case by myself or yourself, and or vice versa. Not sure what is worth. So different entities. And the idea here is that we can acquire the host part by this duplication part here. And the routers, which are configured by another entity, well, they could help me obtain the prefix. That's an alternative to DHCP. So if a router is here in my subnet, and this router knows it has to serve as a default router for everybody at home, then my host can discover this, instead of having me to type in what is the next hop router information. So it will send a packet to all routers that are on link. So there is a multicast address for all routers that are on link with IPv6. It will ask, are you willing to be my default router? If the router says yes, typically there's only one router and it's always willing. So it will reply with what is the subnet prefix. And then the host has the subnet prefix and its host address. So here you go, bingo, you have a full address and you can work and belong to the internet. Voila, we'll do a break and resume at 1:15.